Yeah, hello. Welcome to the second video on exploration strategies, and in this video we will be talking about classical exploration strategies. Okay, so this is our agenda that we follow along through this lecture series. So in the last video we actually talked a little bit about the motivational issue of exploration and reinforcement learning. We formally defined the problem and we introduced the concept of multi-armed bandits. We also introduced the so-called regret. Actually, regret is, remember, the difference between the optimal action that an agent takes against the action that actually has been executed. In this lecture, we will actually introduce mathematical concepts to do exploration under optimal regret. Okay, so let's get started. So the first thing that we also actually introduced in this lecture was epsilon greedy exploration. So if you remember epsilon greedy exploration, the general idea was actually that we take the best action most of the time, but occasionally we do something completely randomly. We did this in order to guarantee that we actually see all the important things in the state space. How can we actually formulate this in the bandit setting? So actually this means that action values are estimated according to the past experience. So we average the rewards that are associated with the action up to a time step t that we're currently considering, meaning that the actual Q function, or actually the action value, is actually 1 over the number of times we actually have evaluated this action, and we have some indicator function here that just sums up the rewards that we got if the action that we have been taken was the current action. So exactly in here. So I is a binary indicator function that nt is the action selection and nt is the action selection counter. So, and what we actually did is, with a small probability epsilon, we actually took a random action, so meaning that we explored the state space, and with a probability of 1 minus epsilon, we pick the best action that we have learned so far. So we want to exploit the state space. So actually what we did is, in the usual exploitation case, we took the action that currently maximizes our Q function. And with epsilon greedy, we introduced epsilon greedy as an easy solution to do something. However, the question is, if we want to do random exploration occasionally, the question is this actually enough to do? So is this actually guaranteeing us anything? And can we then be sure that we actually explored the state space well enough? And the second question, actually, when we try to answer this question, is the probability of epsilon, meaning that we do the random exploration. How should we actually pick epsilon? And that's really a question that's not so trivial to be answered. Okay, what's the main motivation behind this? Or actually, if we now consider a little bit more what we actually promised, that we want to look a little bit about on the regret such strategies have. What we actually did is, in the beginning, when we assume, okay, what is the regret of a greedy action? So just imagine that we have some knowledge on our Q function, and we just select actions greedily. So in such cases, actually, greedy may select a suboptimal action like forever, meaning that greedy has a linear expected total regret. So you could imagine if you remember the formula of the regret, it's just if we are never taking the optimal action, actually, so the per action regret will always be static, and we keep on using and actually selecting this action, meaning that the visitation counter of this action is still increasing and increasing over the time steps linearly, meaning that greedy has a linear expected total regret if we do greedy exploration, or no exploration in this case. So in contrast to that, epsilon greedy continues to explore forever. So there is a static probability of 1 minus epsilon that we actually select an action that is the argmax over our current knowledge. So it's the argmax over our current Q function. However, with a probability of epsilon, it selects a random action. So in a sense, this means that epsilon greedy will continue to select all the suboptimal actions with at least a probability of epsilon over the number of actions that we actually have. Even though we actually know a lot about our Q function and we already have good Q values for some of the actions, we always will keep on selecting actions that are really not optimal, that are suboptimal in a sense. Meaning that if we're using epsilon greedy with a constant epsilon, we always see again a linear expected total regret. So I think that's in a sense somehow also intuitive. So we'll also, as we keep on introducing the algorithms in the upcoming slides, we will actually resort to a little bit of an implementation example. So what you see in here is actually a Jupyter notebook that's gratefully provided by Lilian Wang in her GitHub repository. You will actually see the link in here. So if you go and click on this link, you will actually find the original source code of this Jupyter notebook. I adapted a little bit, things only a little bit to make them a little bit more adaptive to the lecture in here. So what do we actually have here? We have actually an implementation of a Bernoulli bandit class where we just defined the multi-armed bandit as we introduced it in the last lecture. And then we have what we then actually have is a solver class. A solver class is actually like a parent class that implements the bandit strategy. So so we have actually the solver class that actually keeps track on the counts and the actions that are actually available. It keeps track on the regret and also on the history of cumulative regret. It can update the regret. In a sense, this is just a helper class, and it actually provides an interface to return the estimated probabilities, so the thetas actually that we introduced last week. However, this is overwritten in the certain implementation of the classes. Actually, the same with a run step and here a run class, but however, I will go into the implementation of the subclasses immediately. So, okay, so let's talk about epsilon greedy. This is the algorithm that we're actually currently discussing. Epsilon greedy is implemented in here. So from the definition, epsilon greedy is just using something like initialization of the initial probabilities. So in this case, it's just 1 and an epsilon, meaning that this is the exploration parameter. Epsilon is the probability to explore each type space, and initproba is an optimistic initialization in this case. But you could actually use also something else. Okay, so and what we actually do is, if we run epsilon greedy, if we run the epsilon greedy solver, what we actually do is, given a current time step, we just take a random number. Here we get a random number between 0 and 1, and we just evaluate if this random number is below our epsilon, and if it's our epsilon, we do a random initialization, meaning that we set an index I that provides just a random action over our actions that we actually have, and if the random number that we actually sample is not below epsilon, then we pick the currently best action that actually maximizes the current set of actions that we actually have, our current belief. Then what we do is we actually take this action in here and generate a reward from it. This function is, I think, implemented also in the so somewhere below. So we actually generate a reward from it, and so according to the probabilities that we actually have provided below, so we initialize everything below, and we generate a reward from this taken action, and we update our estimates according to the function we have saw in the beginning. This is just an increment over the current mean that we actually keep on track. Okay, so actually then there is a lot of other implementations for the algorithms that we will keep on exploring. What we now can actually parameterize is the number of slot machines. So we actually in this example assume that we have 20 slot machines to play with, and we play over a horizon of 10,000 time steps. We initialize the Bernoulli bandit with a number of slot machines, and we actually have some test solvers that we actually will use who implement actually a little the exploration strategies. However, I commented all of them out except epsilon greedy because that's what we're currently interested in. So we have the test of it is just the names for the plotting, and let's just maybe run the notebook completely. So kernel run all. So let's just see what's happening. So everything is executed already. So and what's being plotted here is actually over the time steps. So actually the training time steps of evaluating and running the bandits, which is actually 10,000 as we did it. You see actually the cumulative regret that the agent actually sums up to. And what you actually see, you see a linear line. This is because actually this is actually what we introduced. So the cumulative regret or the expected total regret of epsilon greedy is actually a linear one, and it's the linear one, and it's somehow connected to epsilon, which is actually our exploration parameter. So our regret is actually bounded to epsilon over the number of actions. Here you see the number of actions, so it's 20. We have sorted them by their probability, and what you see is after the end. So actually the blue line is somehow it's the ground truth, and the blue dots of the blue crosses are what epsilon greedy assigns as a reward probability towards those actions. And you see that after 10,000 time steps, epsilon greedy does a decent job in predicting the probability of the associated rewards. And here you see actually a histogram of the number of times that epsilon greedy actually selected such an action. There is like a small peak, I think, for action number 3, probably because the reward probability of the action number 3 is close to action number 1 or 2, which is actually the peak. So 2 is actually the peak in here, and you see it. However, there is also like action number 4, which is really like very close to the perfect action, and it takes a while for the agent to actually go to the correct so for sometimes actually he thought that this is the best rewarding action. However, at some point it turns out that this is actually action number 2 is actually the best one to go. So let's get maybe back to the presentation at this point. It's in here. So what you see now is we have seen that epsilon greedy and also greedy has, we can like also plot it for the greedy action 2 already. So we see it in here, so we can like include this one, so epsilon being 0, a full exploitation agent. And what you see is also like, although being very different, that the full exploitation agent also has a linear regret. However, it exploits already everything that he has seen. Maybe just run it again and see if it makes any difference. Just feel free to also like implement to download this notebook and also play around with it a little bit, that you can actually get an intuition about how these things are actually working if you look if you implement them. Okay. So actually, yeah, you see actually depending on how much time steps and how much how good randomness is actually happening, you see that both of them actually have a total expected linear regret in this case. And what you also see is that while being very competitive while full exploitation is very competitive over epsilon greedy, you see that the estimation of rewards it was just luck actually, because it actually covers the best probability. However, it does not do a decent job in estimating all of the probabilities well. Okay, so let's go back maybe now to the presentation, or actually let's go back to the to our. I have to like maybe put this window completely away so that it's not disturbing. Okay, yeah, so epsilon greedy as well as greedy, they have both a total a linear expected total regret. So this is the demo for it. Please download it and check it out. And also play around with the implementation. It's really nice, applicable, and accessible, I would say. Okay, so far. So random exploration actually allows us to try out options that we have not much knowledge about yet. So, however, due to the randomness that is actually introduced in the epsilon greedy strategy, we in the end up exploring bad actions all over again. So this is actually what we have seen. Epsilon greedy does a very good job in estimating the probabilities. However, it keeps on exploring forever. And the question is, what can we actually do about it? So there's actually one thing we can do, and one things that is actually implemented in all of the framework environments too. We can just decrease epsilon over the course of the training. We saw in the demo that this helps. We didn't see it yet, but however, I can also show this to you. So if we like go to the implementation in here, I will give you the plot again. If we like go in here and I implemented an epsilon greedy algorithm in here. So if you like have the epsilon greedy, the one I remove the full exploration thing because it's disturbing. And if we go again, you can actually see that while you have an epsilon greedy with a total with the expected total regret, we can actually anneal epsilon and get an asymptotic performance. However, it's not very well plotted in here, so you actually don't see it very well. Maybe if I reduce the number. Okay, so you actually see that in the beginning there is like a decay where actually in the beginning there is like a bigger epsilon and we decay epsilon over the course of training. In this case I configured it like it is implemented in the framework environment. So you have some exploration fraction with us, which is just 1% of the maximum time step. So for the first 10 time steps, we actually keep on exploring. We can actually do this maybe to 100, and finally we want to have an exploration of 0.1%. So if we run this, we see that in the first 100 that our epsilon decay is within the first 100 time steps, and you see that there is like a regret. However, the regret is actually asymptotically decreasing at this point, and here we have a linear regret that depends on our final exploration rate. So if you run this for different configurations to see actually how things are different due to the randomness, you can also see that things like this. So it actually you have some asymptotic performance in here where you decay the epsilon, and then you have a linear performance when you keep on doing a little bit of epsilon greedy, in this case only 0.1%. Okay, so this now for this. So we actually see that decreasing epsilon over the course of training might work at the end. However, it's not really easy to tune the parameters very well. So if you have implemented, if you have played around with, for instance, DQN or PPO examples, or more like for DQN, if you implement this on favorite Atari games, you will see that tweaking epsilon is a very serious thing to do. So actually, we see that this is working. However, it's not really satisfying to do it. However, another option would be to be more optimistic with options to be with high uncertainty, meaning that we should be optimistic with options that we are very certain about. Meaning that meaning that we have actions that we are already very confident because we actually always we sampled those actions a lot already, meaning that we can be very confident about the value from them we have. And those actions that we did not evaluate so much, because with them we are a little bit uncertain, we want to explore them. So we do not really need to explore actions that we have explored a lot in the past. So in a sense, we want to prefer actions for which we are, so if we talk about exploration, we want to prefer actions for which we do not have a confident value estimation yet. So that's actually what we want to have. And because actually those have a great potential of be high rewarding in the end. And an idea that actually implements this one is called upper confidence bounds. And we will introduce them in here. So the idea of upper confidence bounds is actually to estimate an upper confidence. It's called ut of a for each of the action values. So it's defined over all of the actions over the course of training t, such that with a high probability we actually satisfy these inequations. So we want to actually find an upper bound that with a very, very high probability defines the upper bound to our true Q value. So this is our sample estimate that we currently think it is, and we want to define an upper bound that we put on top on our sample estimate. And what we actually want to do, we want to have with a very, very high probability, we want to have this value being greater than the actual value that we cannot access. And just imagine for a while that we actually know this upper confidence bound ut. Then the thing is easy. So then we can just say select the action that actually maximizes this equation in here, and this is actually the action that maximizes the upper confidence bound. So this is actually the action that we wanna take in order to implicitly explore those states for which we are not so confident. Okay, now let's take a closer look more about how is this upper bound confidence ut defined. So what is the requirement to such an upper bound ut? So in principle, the upper bound ut should be a function of the number of trials and t of a. So actually it should be somehow connected to how often we actually already chose a. And what we also want to say is if we have a small visitation counter, so actually if we tried out a not so often yet, we want to have a large bound ut. So actually we want to say that in a sense that the current value estimate, it is uncertain. We do not know so much. We did only take a few samples of this action, and we are not very certain about it. So we want, in this case, we want to have a large bound. In contrast, if we already visited or if we already tried out an action A very, very often, we are very certain about, or we are very certain that our current estimate of the value of this action is actually very accurate. So we want actually the bound to be very small, such that the argmax in the end somehow becomes the sample estimate of the Q function. By the way, this should be Q hat at this point. However, okay, so this is basically how things should be connected. The question, what can we do about it? There is also another thing that's called the central limit theorem. It's considering the thing of uncertainty over a number of trials, and it says that the uncertainty we have in an estimate of a random variable, it decreases as the square root over the number of samples that we have drawn from this distribution, as long as the variance of the rewards in this case is bounded. So you can, like, if you're interested in this one, you can look it up. However, the uncertainty decreases with the square root over the number of trials that we take. I think this is at some point, this is somehow something intuitive. And the question is now, how can we efficiently estimate the upper confidence bound? Before we do this, actually, let's put all the side notes again on a single slide first. So actually, we want to minimize, this is the regret, so we actually want to minimize the sum of the visitation counter of an action times the per action regret of this action. This is actually what we want to minimize, which is basically the cumulative regret in the end. If the per action regret is big, we want the visitation count of A to be small. If the visitation count of A is big, we want the per action regret to be small. However, not all visitations of A can be small. Why is this? Because actually the sum of all NTs in the end is exactly T. So actually in the end, the visitation counters of all of our actions is actually equal to the number of time steps we have currently run. We know NT of A actually, because we actually executed the action. However, we do not know the per action regret. But the question is, what can we learn about the per action regret? And in order to put this in context, we need some prerequisite first, and this prerequisite is called the Hoeffding's inequality. Maybe let's just go through it. So in the Hoeffding's inequality, this is defined over or looks at the probability of or of a certain event happening given some underlying probability distributions. So in the sense let xy, x1 until xn be identically and independently distributed random variables whose values are between 0 and 1. So it's like the Bernoulli setting that we have. And let also xt be the sample mean over the probability distribution. So actually we sample from a random variable and we actually can estimate the sample mean by taking all the samples and calculating the sample mean. Then the Hoeffding's inequality says that for any u that is greater than 1, that the probability of our expectation over x is greater than the sample mean plus some u is actually smaller, is bounded actually by e to the power of -2 times t times u squared. Meaning that it just describes a relationship on depending on the samples we draw from a probability distribution, it describes the probability of a random variable x being the sample drawn from a probability distribution is below some value. Okay, to put this into a context, the question is, for instance, in this case, how likely is it to achieve? By the way, this example is borrowed from the German version of the Wikipedia page on Hoeffding's inequality. So the question is, how likely is it to achieve an I-sum of at least 500 when we roll a dice for 100 times? So this is the question. And what we then define is, okay, x is a random variable that actually describes the result of a roll, and its mean, we know it's actually 3.5. So that's actually the mean of the distribution because we can take values between 1 and 6. And if we like now reformulate it a little bit towards what we have in here, so actually the random variable can be defined like this. So the sample minus the expectation is between -2.5 and 2.5. And now we can actually calculate the Hoeffding's inequality, meaning that the probability that our random variable takes in the end a value of more than 500 is nothing else than the variable minus the expectation is more than 150, meaning that what is the probability that the sum of all the i's is by 150 larger than its expectation, because the expectation in the end is 350. And we can actually put all the values in. This is just a normalization step. Actually, we can omit this in our example because we have a Bernoulli example with 0 and 1 in here. And this is somehow disconnected a little bit because we have bounds in here. This is just a normalization that you can actually throw away in the usual setting where we actually do exploration. However, we can take e to the power of -2 times the number of trials and u squared, and you can actually bound it up, and you see that the probability of having really like a sum of more than 500, it becomes really, really small. So this is actually Hoeffding's inequality, and actually now it arises the question, how can we actually use Hoeffding's inequality in the upper confidence bounds? So let us just apply Hoeffding's inequality to the bandits with a bounded reward setting. So given one target action A, let us just consider that RT of A are the random variables, QA is the true mean, Q hat T of A is the sample mean, and U is the upper confidence bound, U is equal to UT of A. From this just follows the following equation. The probability of the true mean being larger than the sample mean plus the confidence bound is lower than e to the power of -2 times the upper confidence bound in here. And what we now actually want is, we want to pick a bound UT of A so that with a high chance the true mean actually lies below the sample mean plus the upper confidence bound. Meaning that e to the power, so the right part of the equation, should be a very small probability. So if we define the probability, so we define a tiny threshold p, then we can actually solve for UTA, meaning that we can reformulate this one. So e to the power of minus 2 times t times UTA squared equal to p. We can set our upper confidence bound to actually this value, meaning that it is the square root of minus log of the threshold divided by 2 times the number of tries we already took this action. So this is actually defining the upper confidence bound of A in this case. Yeah, so maybe look through this video again. However, I think while the formulation about Hoeffding's or across Hoeffding's inequality might be a little bit unintuitive first, I think defining the upper confidence bound as such a term is like very intuitive, because you have actually a term that has the square root, meaning that that is actually describing the uncertainty, how it is decreasing. You have in the denominator the number of trials you already took this action, and you have in the denominator some small probability with which Hoeffding's inequality in this case should be satisfied. Okay, so one more thing about the upper confidence bound. With collecting more and more samples, we will actually get more and more confident with time. So let's do now again a little tweak. So because actually what we could do in practice is we can reduce P as we observe. So actually our threshold P can actually somehow be connected to the rewards we are actually getting from the environment, meaning that we can in some way define the probability, the threshold P, sorry, not a probability, the threshold P over the course of training, meaning that we can say that our small threshold P is just defined by 1 over T, meaning that it is decreasing very, very quickly over the course of training. If we set P equal to 1 over T, we can actually come up with something like this. And this is actually ensuring that we always keep exploring. However, we will select the optimal action much more often as T is actually approaching infinity, because this actually leads then to the fact that the confidence bound is really, really decreasing over time. Yeah, so one fact, there is an algorithm called UCB1 in the original paper where it has been implemented and proposed, and UCB1 actually in their implementation proposes to use uses a threshold of T to a power of minus 4. If you then plug it into formulas, you come up with something like this. So UT is equal to this one, and you can actually plug this into our action selection strategy, where we actually take the argmax plus QA plus the confidence bounds, which is actually an augmented version of the Q function, which actually helps us to select the actions from which we are uncertain about yet if we have an underestimated Q value, even if we have an underestimated Q value. So if we have an underestimated Q value, this means that this value becomes high, giving him a bonus such that we will eventually select this action and get new information about it. Also, one thing to mention, we could also insert a hyperparameter C in here to adjust the weight of the bonus component a little bit. Okay, so in this case, UCB with a C of square root of 2 has a logarithmic expected total regret, and we can also play around a little bit in the demo also with the upper confidence bounds in here. So I will again share the Jupyter notebook, and what you see in here is we have still our 2 bandits in here involved. We can like include the UCB1 bandit. So the UCB1 bandit is defined with just B, and is hard coded, I think, to have a C equal to 3. Let me just see in here. So UCB1, no additional C at all, so it's just taking 1, not a problem. But feel free to play around with it a little bit. And if you like implement this one and run it, then you will see that over the course of training, in this case, it's not like having a decay in epsilon greedy strategy, but what you see is like you see a logarithmic asymptotic behavior of UCB1. I can also maybe increase a little bit the time so that you can see the logarithmic regret a little bit more closely. Okay, if we, I mean, I think you saw it. We can like even put this a little bit further. Now it's taking a little bit more long. However, you'll see that you have an asymptotic performance with UCB1, and it really decays over the course of training when it actually reduces the uncertainty over the estimations. And you see they do a really good job in estimating the true probabilities. So, okay. Okay, so that's it. So UCB works really well because it actually somehow incorporates the uncertainty we have over the current rewards that we're actually expecting. However, in UCB, we did not really assume any prior on the reward distribution. Meaning that the Höfling's inequality really follows a relatively pessimistic bound. And the question is, maybe we have some prior knowledge about on the distributions of our rewards actually, as a per action rewards. And if we actually have some prior knowledge on this, we can also use this information to actually allow for a better bound. So prior knowledge would be maybe something that you know actually that the rewards stem from a normal Gaussian distributions, and you can somehow describe their distribution by mean and variance. So if you know a lot about it, you have maybe a large you have low variance, and if you know not that much about it, you take some mean and take a large variance. So in a sense, what we could actually see is, or what we can actually do is, we could like expect the mean reward of a slot machine that we have in the beginning to follow some independent Gaussian distributions. And if we would allow for this somehow, or if we assume this, we could also set the upper bound to something like a confidence interval, and then set the upper bounds ut of a to be something like twice the standard deviation of the Gaussian distribution. However, meaning that we need to actually fit a Gaussian distribution to our current samples that we get. So what we actually now had in the beginning, or what we until now actually did, is our bandits held some belief about their current sample estimate of the true rewards. Now, if we are now fitting something like Gaussian distributions, theta is no longer being something like the sample mean over the rewards. However, it now represents something like a parametric distribution over the rewards, meaning like a mean and a variance from a Gaussian. Meaning that now, instead of really keeping track on the sample rewards that we get, we model distribution over where we think the true value is and not actually where the rewards have been. And whenever we get new information, we can update the parameters using the probability of the rewards under our model. And this we can actually do with Bayes' rule to update the distributions. Yeah, so actually there's actually two things we can do. So if we have actually a parametric model of our distributions, we can actually estimate, and we can actually calculate our models and use the posterior to guide actually the exploration. We can do this in an upper confidence bound way, which we will actually provide in this extension in the current slides. But we can also do it with Thompson sampling and actually match the probabilities, which we will also like introduce in the end of this video. Yeah, so actually in upper confidence bounds, so far, or like to put it a little bit ahead in contrast to Thompson sampling, in UCB we do not match the probabilities of the rewards that we want to update. However, we update our belief of the distribution and our belief where the true value is, and we update the parameters of the distribution. So this is actually what we do when we do the UCB kind of a Bayesian way. Okay, so let's maybe start with an example. So again, consider a Bernoulli distribution, and our rewards are either 0 or 1. So like everything we did so far, and assume that our prior is something like a uniform distribution being 0 and 1, so each mean reward is equally likely, basically meaning we have no idea and we think that everything could happen. And if we talk about Bernoulli distributions, it's a very intuitive and a natural way to use a beta distribution actually to describe the posterior. Actually, beta distribution is defined by two parameters, alpha A and beta A, or alpha and beta. Within this, which actually, if we start with the uniform distribution, so if we set the prior to be a uniform distribution, we just set initial parameters alpha to 1 and beta to 1 for each of the actions. You will see this in the next slide. I have a small animation on it. But basically what the beta distribution describes is how often did you see A and how often did you see a 0 and how often did you see a 1. And for mathematical reasons, you actually need to add an offset of 1, meaning that you interpret it with, in the beginning, you didn't have seen a 0 and you didn't have seen a 1, meaning that you just assume a uniform distribution in the beginning. Okay, and if you update the posterior, so actually you want to update your function based on new data you actually sampled from, this is really embarrassingly easy because you just increment alpha if you see a reward of 0, and you just increment beta if you see a reward of 1. So this is really embarrassingly easy. Usually if you do a Bayesian update, you're usually concerned with something like intractable posteriors and integrals and things like this. Here it is really relatively easy. Okay, so let's maybe go to this slide. Here you see a little bit, this is also a nice animation that I borrowed from the Wikipedia page. You see for different parameters of alpha and beta, you see actually how the beta distribution looks like. And if you, I don't know if I can actually make it stop. No, I can't. However, you see that if alpha and beta is equal to 1, you have a uniform distribution in here. And if alpha is like greater than, is lower than beta, you see that 0 is being more likely and beta is beta is larger. You see actually that the other value is much more probable. But maybe let's make an example out of it. So here you see actually two snapshots of the beta distribution, and just imagine that we see some rewards over the course of training. We have a time horizon of 4 in this case, actually meaning that we see 4 rewards in a sequential way. The first reward is 1, the second is a 1, the third reward is a 0, and the fourth reward is also 0. And in the beginning we have not seen anything, meaning that alpha and beta are actually initialized with 1. And the posterior looks like this. So this is actually the distribution of our beta, and meaning that everything is equally likely. However, if we see a reward of 1, actually this means that we increment beta for a little bit in here. And this is actually how then the posterior of the beta distribution looks like. It assigns a much in probability of this action to be a 1 than being a 0. You see that even if you're going one step further and you get another 1, you actually have a beta distribution that's parameterized by an alpha of 1 and a beta of 3, which makes a 1 even more likely. However, you have still some uncertainty because actually there is also something in between where you can actually say that a 0 is not completely off the table. Then if you once receive a 0 in here, meaning that you have received 1 0 and 2 1s, meaning then alpha is equal to 2 and beta is equal to 3. This makes something like a Gaussian shaped distribution with a little shift to the 1. So it's really certain, or there's much more probability mass near to 1. However, you still can see there is a lot of uncertainty in actually knowing what's happening in here. And if you actually have seen 2 zeros and 2 1s, you see there is an equal distribution of having a 0 and a 1, meaning that the mean is at 0.5, exactly in the middle, and we have a symmetric distribution over beta. Okay, so by the way, all of this is just for a single action. You usually have 1 beta distribution per action. And actually you see how the beta distribution is updated through the Bayesian principle over the course of training. And you see that the uncertainty is covered really nicely and well in here. So the question is now, what can we do with it now? And usually what you do in practice is you compute the posterior over the action values, so all of them, and then you estimate the upper confidence bound, for instance, using something like you take the standard deviation of your distribution and you just weight it by some hyperparameter C, and this is actually what you use as the upper confidence bound in your algorithm. And then what you can just do is you pick an action that maximizes QT of A plus the parameterized standard deviation, which is actually something like you can easily implement in a UCB type of way. This is also implemented in the Jupyter notebook that is provided. I will also give you a small feeling about it. So in here we just have to, in this case, just have to refill the Bayesian UCB in here. The parameterization is like 311, meaning that we have a C of 3 and we initialized A, also alpha and beta, each of them with 1. So in this way, also in this setting, the hyperparameter C is equal to 3. And if we run this again, sorry, I still left the 15,000 samples that we actually draw, that we actually take through the course of training in here. Maybe we can in the meantime look a little bit on the code. So what you see in here is we just pick the best one of the action considering our current upper confidence bound. So we just select the action that maximizes this equation in here. This is nothing else than what I have on the slides, although it's looking a little bit more complicated depending on the data structures. And this is the really nice thing about it. In order to update the Gaussian posterior, we just need to make the increment using our rewards, which is in this case 1 for the one and 0 for the other. And this is just the update. And then we can start over again. And I think it's done by now. You see that using priors of the probability distribution, so approximating the rewards through beta distribution, allows for a much more efficient exploration. So you actually see that the cumulative regret of our bandits, of our agent, of our Bayesian UCB agent, is much better than everything that has been so far. However, I mean, you have some uncertainty on lower ranked values in here. However, even with their sample mean plus their standard deviation, it will not outperform a value that it gets in here. And this is the important one. It should select. It should have a very good certainty about, or a very low uncertainty about highly likely and high rewarding actions that we can actually take. Okay, this is the UCB version to actually use Bayesian principles and prior distributions to update beliefs to guide exploration. There's also a second idea that actually uses the idea of modeling the belief through beta distributions, but not with a upper confidence bound fashion, but via direct probability matching. So many people, and also me, I also find it a little bit unintuitive. However, if I really dig through it and see the implementation and try it a little bit out, it gets also clearer for me. So I really encourage you to do the same, as I do. Okay, so the actual idea is what we also can try is we can try to directly sample the action. So what happens if we directly sample the action from the distributions? So the idea is, this sounds a little bit crazy, but the idea is we select an action according to the probability that A is the optimal action, given the history of everything that we have observed so far. This is like a little bit formal of what's happening. This is actually what we want to do. So we want to actually take the Q value that is maximizing this one according to all the history we have seen so far. And the idea is we can do probability matching via Thompson sampling. And I will just line out a little bit something like a pseudocode or like a receipt to do this. So first, we assume that our action values are actually following a beta distribution for the Bernoulli bandit. So this is actually the same setting as before. And QA is nothing else than the success probability of theta. Beta AB is within an interval of 0 and 1, and alpha and beta relate to the counts of success and failure, which is actually what we did in the beginning. What we then do is we initialize the prior as we also did before, alpha equals beta equals 1 or something different, so what we think it is. However, if you have no idea what to do, just initialize it like this. And now at each time step, we sample an expected reward QA from the prior beta distribution for each of the actions. So for each of the actions, we just sample from the beta distribution and look what is the expected reward of this action, and then we select and execute the best action among such samples. So we just see what's actually the sample reward of each of the actions. We just select the action that maximizes the sample reward. And now, having done this, we observe a new experience, and this new experience we can actually use to update the beta distribution of the action from which we sampled from. So the question is now, how is this actually working and why this is working? So if you imagine actually so what helped me a little bit is to think about the two cases. The first case, what happens if we overestimate the reward probability once during the training, and what if we are underestimating it? So if we are overestimating the reward probability of a certain action, this will actually lead to the fact that we will more often get samples from this, that we actually get more often samples that maximize this action that we actually should. So we actually, the probability is higher to actually take this action and select it. It outperforms the true probability. And if we do this, we actually get experience from the real world, which actually allows us to see that we're actually overestimating it. So we're actually correct for the overestimation problem. So if we are currently overestimating it, the chances is higher that we get a sample from this distribution that outperforms the other ones, and we get experience that actually pushes it down again. So this is not a problem. What happens if we are underestimating the reward probability? So if we are currently underestimating it, there is still a chance that we actually get high values out of this distribution. And so actually when this is the case that we underestimate the reward probability. So this is actually in very rare cases where we just get 1 or 2 samples and that are really, really low, meaning that we still have a high variance on the beta distribution. So we can really see there is still a large chance to get by chance a value out of this distribution if we sample from it that maximizes the argmax operator, and we still take this action. And if we still take this action, the chances become high actually that we correct for the wrongly configured parameterization of the beta distribution, meaning that we correct for the underestimation problem. So actually this helped me a little bit to understand how Thompson sampling and probability matching is working. And one thing to mention, of course, we update the beta distribution accordingly as we also did it in the upper confidence bound fashion. So it's really embarrassing. We just add with the indicator function to alpha or beta respectively. And if we did it, we can proceed and go on at each time step and sample the next expected reward again. Okay, so we also have an implementation of that one. This just requires that we need to make the comment out so that we can actually run it. I'll just run it again. I know it takes some time, but in the meantime, we can look at the source code. So what you actually see that the source code to implement Thompson sampling in this way is actually really neat. So you do not really have to do much about it. So this is the posterior update in here. It's as the same as we did it in the Bayesian UCB. And what we do here is we just sample from all of the beta distributions. We just take a sample per distribution, per action that we actually have and maintain. We maximize over this one, so we take the distribution that provided the maximum value, and we use this action and generate a reward out of it. And this reward is just then updating the beta distribution of the respective action. So and this is it. And if you do it like this, we can run it again, and the probabilities will actually converge to the real probabilities. So this is actually what's happening. And if you do like this, you see that Thompson sampling even outperforms the Bayesian UCB in here, because it directly works on the probabilities without having an estimate of uncertainty or explicitly using something like a standard deviation on that. Yeah, so this is actually very nice, because for Thompson sampling, you do not really need to configure that much. You just need to provide the prior. There's no hyperparameter involved, and this is it. And you get something like the same as out of UCB. So it's like using the same principle in order to using a beta distribution induced as a prior to modeling the reward distribution, and then the update of actually how you actually estimate the probabilities is different from UCB, and you see that it's much better, or it can be much better in practice. So okay. So this was the demo on probability matching. You saw the link of the GitHub repository where you can actually download this Jupyter notebook and you can play around with it a little bit. Okay, so what's it for the summary? So let's maybe sum it up before we actually dive into exploration in DeepRL in the next videos. So actually, to summarize it a little bit, we need exploration because information is a valuable thing. In terms of the exploration strategies, we can either do no exploration at all, so we can do a greedy thing, which is only focusing on short-term rewards, or we can occasionally explore something at random, which is something that we have seen with epsilon greedy. Or we can even do more on it. We can actually explore and actually pick actions where we actually are highly uncertain about, and we favor actually those actions that provide higher information gain. There's also, by the way, there's also like material that's really talking about information gain with an information theoretic point of view. You can find more on it, for instance, in Sergey Levin's lecture. So you can actually do a smart exploration. What did we not cover in the basic classes so far? There's also something like Boltzmann exploration, where the agent draws the action from a Boltzmann distribution, so a softmax distribution, over the learned Q values, regulated by temperature parameters. So this is also like very interesting to look into. However, we didn't really introduce it in the lecture because we do not need it also in the DeepRL version of it. And we also didn't talk about what happens if policies are actually approximated with neural networks in here. What we do there usually is we encode something like an entropy loss term. This is also something that I have shown you where we talked about policy gradients. We can actually add an entropy term H over the probability distribution provided by the policy. We can do this, we can include this into the loss function, and this actually encourages the policy to take more diverse actions. Or we can actually do noise-based exploration, meaning that we can add noise into the observation, into the action, or even into the parameter space. So this is something that's also included in current implementations of DQN and DDPG. So you actually you can actually disturb the parameters of the network a little bit. You can disturb the actions a little bit, or the observations a little bit. So this is actually something that we did not really focus on this class. However, we will use a lot of what we learned in here actually in order to draw conclusions to the DeepRL versions of them, which are much less theoretically analyzable.